Good Monday morning, everybody. It is Monday, March 23rd. Welcome back from spring break, or back as we're going to be. Today we're going to start Module 13, which is a very short module. It's on exponential functions. We will first graph exponential functions. There, see? And then we will do some word problems. We're going to take a look at the parent function, which is y is equal to the b raised to the x. That makes it exponential function because we have a variable in the exponential position. We will then take that and transform it into our normal a, b, h, and k. And it gets a little confusing because we have our regular small b, and now we have this capital B. This capital B is just the base of the exponential function. Can be any number. Can be 2, can be e, could be pi, could be 1/3, any number. Not sure we learned that yet, but we'll get to it very shortly. All right, so we're going to do, before we do transformations, we'll take this basic parent function and see what it looks like. So we'll put in some x and y, so we'll go ahead and put a 0 in there. So y is equal to the, well, I guess we can't do b. Let's make another function here, base 3 to the x. So we'll go 3 to the 0. And as we've learned before, anything raised to the 0, well, just about anything is 1. Let's go ahead and put a couple values on either side then. So y is equal to 3 to the first. Of course, that's going to be 3. So let's take a look over here and start to see what this graph is going to look like. That's not a real good graph. All right, 0, we are up 1 unit. Over 1, we are up 3. And if we go to 2, this is the power of exponential growth. And it becomes a 9. So that's going to be way up here. So this graph is rising quite quickly. A lot of things grow exponentially. Money, bacteria, coronavirus. Let's go the other way. -1. Y equals e to the 3 to the -1. We know that can't be evaluated, so it's 1 over 3 to the first, or 1/3. So very quickly it's coming down now. And if we just go out to -2, go ahead and put these values in here, and that becomes to the 1/9, or 1/9 rather. And it's getting much closer. The further out you come, the closer and closer it gets, and we know that is called an asymptote. It never reaches the x-axis, therefore y equals 0 is a horizontal asymptote. And that's what the parent function looks like for the exponential graph. The domain, because it's going off in both directions, is unlimited, so it's a set of x's such that x is an element of all real numbers, or written in interval notation, of course, -infinity to +infinity. The range is limited by the asymptote, just like we saw with our rational functions, so it's either from the asymptote up, or if it was a reflection down, from the asymptote down. So this is going to start at 0, non-inclusive, and go up to infinity. Okay, let's take y equals -3 to the, I don't know, x minus 1 plus 2. So we're going to list our transformations, a, b, h, and k. A being out in front of the 3. The 3 is my base, so a is a -1. It gets a little confusing, but the 3 is not your a. That, of course, is going to be a reflection over the horizontal axis with no stretch or compression. B is in front of x, so that's going to be a 1, which does nothing. H gives me the opposite, so it's +1, which is a horizontal translation to the right by 1 unit, and a vertical translation up 2. All right, so the only two features that we're really interested in graphing are going to be the y-intercept, that 0, 1 point, and our horizontal asymptote. And just like with the rational functions before, the horizontal asymptote is only affected by k. So k is going to go up 2 units. Our horizontal asymptote simply rises up to y is equal to 2. And now we've got to transform the 0, 1. It's a reflection over the y-axis, so it comes down to 0, -1. Not stretched, I would multiply the y value by anything that was vertically stretched, the same with the horizontal. It's going to rise 1 unit then, so it goes up to 0, so I'm at 0, 0. And then, what did I just say? It's going to go to the right 1 unit, so it's going to go over from 0, -1 after its reflection down over 1 unit to 1, -1, and then rise 2 units up to 1. So it's going to be over 1, up 1. And since it's a reflection, it's going to rise to the asymptote to the right and shoot off down negatively. Now we could find these other 2 points, the x and y intercept, simply by letting x equal 0 for my y-intercept and letting y equal 0 for my x-intercept. But for right now, I'm interested in you finding the point 1, 1, the transformation of 0, 1, and the vertical asymptote, horizontal asymptote, y is equal to 2. So, finish it out by stating its domain and range. Its domain will always be the set of x's such that x is an element of all real numbers. And the range will either be horizontal asymptote up or up to the horizontal asymptote. Here we're going to start down at -infinity and rise up to, but not including, the asymptote at 2. So it looks like that in interval notation. Set notation would simply be the set of y's such that y is less than 2. That's not a 3. Trying to draw in between 2 tripods here. Okay, the one thing I do want to mention, if you have a base such as y is equal to 1/3 to the x, how do we get 1/3? Well, if we recall, 3 to the -1 is equal to 1 over 3 to the first. So basically a negative exponent is a reciprocal of the base. So this 1/3 can be written as 3 to the -x. You'll do the problem in this method just remembering that this negative x, a fractional base between 0 and 1, will be a reflection over the y-axis. And there's nothing that will tell you that. You just have to remember that. Alrighty, if you could go to Google Classroom, you will find a worksheet on there. There will be 4 graphs. Do not do the word problem at the bottom. We'll go over those tomorrow. Please stay safe, stay inside, and keep all communication between me and you through Google Classroom so everybody can see all of our conversations and benefit from them. I will talk to you tomorrow.